Warm here, really warm here.
Okay, so
No, the polar vortex is coming.
Huh?
The polar vortex is coming. They're just getting prepared for it.
I'd like to welcome Michael Singer to the KSDA. His talk will be on the general solution of a first-order differential equation.
So thanks for inviting me. So I'm not sure how much of this talk is really original. It came about because there was a much-quoted theorem where I had never seen a proof, and so I tried to hunt it down. And as it turned out, there's, what should I say, an interesting and easy way of understanding the proof using some work of Richard Cohn. So this is dedicated to his memory. So let me start with two examples. So the examples are this differential equation. So I think we can all solve it if you had to. The solutions are, well, there's a simple solution, the function that's identically 0, and then we have a family of solutions like this. And if I graph these, there's the this identically 0 solution. Sorry. And then the family of hyperbolas. Something look like this. I don't mean hyperbolas, I mean parabolas. So this is C. And now so what I want to point out is that this y equals 0 is an envelope. So this guy is an envelope of these other solutions. The second one, y prime squared minus y cubed equals 0. Again, it's not hard to get solutions. We have a solution that's identically 0, and a family of solutions that look like this. If I let C, I'd like to write it a little differently. If C is 1 over D, then this becomes D over dx minus 1 squared. And what does this look like? Well, again, we have this 0 solution, and the other solutions look something like this. And it's not so much an envelope anymore, and in fact, this solution is a limiting case of this as d goes to 0. So y0 is somehow embedded in this analytic family. I'm going to call this yb. So what do you mean by envelope?
That's not important.
So by envelope, I mean I have a family of curves, and something is an envelope if it is tangent to a unique curve at each of its points. And at each point, there's a curve whose limiting behavior becomes tangent there. Hoping nobody would ask. Okay, so the question is, how does differential algebra distinguish these two situations? What does differential algebra have to say about this? So let me just review a little bit about differential algebra. I think most people know this, but it's a pretty story, so it's well worth repeating. I'm going to be working just with ordinary differential fields. Differential field, and they'll all be of characteristic 0. Of course, we have a ring of differential polynomials. And if I have a subset of this ring, the usual notation is that this is the differential ideal generated by these, and this is the radical differential ideal generated by these. And we know in this situation that this is just the radical of the differential ideal. And we know lots more, that in fact any radical differential ideal is of that form for a finite set. Differential ideal is of this form where this is finite, and this implies in particular that any radical differential ideal can be written as the intersection of prime differential ideals. These pi are prime differential ideals. I'm going to write that, and this is minimal decomposition. And this last theorem is almost effective. That is, we can find, so in general, we can find pi such that, except that we can't always, we don't know how to verify that condition. So we can find pi so that a radical differential ideal is of this form, but in general, we don't know how to check this condition. Yeah.
I'm sorry, I hate to ask, be nitpicky, but is a unit in there? I mean, one in there? Every time I get, I always get confused.
So this is a field.
Right. But I'm sorry, what am I thinking? I'm sorry, thinking something else. Okay.
So that's that. But there is some good news, and that is if I start with one polynomial, so let's say that P is algebraically irreducible, then we can do this decomposition, and we can find the minimal decomposition. Then we can find the minimal decomposition. For me, this is a high point of differential algebra. And let me say how this is done. So we start with P, of course, and I want to, let's say that y sub n, the ith derivative, this is the highest derivative of yn appearing. I define the separant. The derivative with respect to that variable. This is the separant. And
should the I be indexed by n too? What's yn?
So
The last indeterminate.
it's this one.
okay,
I'm,
right.
so I'm just
Okay.
fixing
He's
that.
choosing
Oh,
that.
I see.
He
Okay.
made a choice.
All right, you make a choice, okay.
And we can write P as this. So what does that mean? This is the set of differential polynomials, so that when you multiply by the separate, they lie in here. Okay? And it's this. And furthermore, if you decompose this guy, let's say t minus 1, that gives the decomposition. And I haven't told you how to find it. These are called singular components. And this guy is called the general component. That's what I call the general component and singular components. And Ritt in the 30s showed two facts. That each of these PIs is again just the general component of a differential polynomial. And he gave a criteria to decide. He gave criterion, that's a criterion to decide if something of this form is contained in something of this form. And the criterion is now called the LowPower theorem. And it's been generalized to the partial differential case, I guess, by Levy and Colchin.
Yeah.
But I'm going to stick with the ordinary case. And in fact, I'm not going to state the theorem because it's complicated.
Yeah.
But I will state a special case, just to give you a feeling for it. And it will be all that I need. So I'm going to look at the situation of one variable. So I'm looking at differential polynomials in one variable. And so it's a differential polynomial. I'm going to assume that 0 is a solution. So when you plug in 0 and the derivative of 0 and the second derivative of 0, you get 0. Let's say that P is not this polynomial. I'm going to write P in terms of its homogeneous parts. Running out of letters. This way. So these are the homogeneous parts. Homogeneous when I'm thinking of y and y prime, y double prime as variables. And in this situation, the LowPower theorem says the following. So this ideal is a singular component of that ideal if and only if the lowest powers, P sub s, this is free of derivatives. So it's just y to the s times something. So that's the special case of the low power theorem, but it gives you the flavor. The lowest powers, something is true about them. The general theorem, what one does is one writes this polynomial in terms of this polynomial in a certain way, and then again, the lowest power when you do that should be just the power of pi. Okay, so let's look at my examples.
Are there any restrictions in S? S can be...
What? S is this. I'm sorry, there are too many S's.
Oh.
It's not a separate, it's a little s.
Right.
It's the lowest,
Oh, I have it right.
what do you mean, restrictions?
Does it have to be greater than 1? No.
I don't think so,
No.
because I'm going to have an example where it is 1.
I see.
No, but it's 0. It can be 0.
So when you write that decomposition of homogeneous, that's like decreasing. So S is
Yeah, S is the lowest. R minus 1 double delta S. So let me go back to the examples. And these examples are worked out by hand in Kaplansky's book. He doesn't mention the low power theorem. You don't need this to do what I'm going to do. But let's take a look. So my first example, P1 was y prime squared minus 4y. The separand, so I take y prime is the highest derivative of y appearing. I take the derivative with respect to y prime. So that's 2y prime, the derivative with respect to that variable. And so if I decompose this, it will be P1, the quotient ideal with respect to the separand, intersect P1 and S. And I'm not going to do the calculation, but it turns out that this guy is generated by P1 and P1 prime. And this guy, well, when I throw this into the mix, I'm going to get y.
Yeah.
And now the low power theorem, this has homogeneous degree 2, degree 1. The low power theorem says that really this is still a singular component. It doesn't disappear, because it wasn't in here. Or I should say, it doesn't contain this.
Is it P prime, P1 prime divided by S?
No, that's the point.
No, it's the basis.
It's really generated by P1 and P1 prime.
Really?
And I'm going to talk about a theorem that predicts that.
Okay.
Right.
That's what I would like.
Then you don't have to put P1 P1 prime because it's different.
Yeah, sure, okay. But I'm doing it for a certain reason.
Right. That's true.
The
differential ideal generator.
I mean, there is no, the ideal is not, it has to be something else because the ideal is not prime, the original one. This cannot be prime decomposition.
I'm sorry, I need to put, so you're right, I need to put S.
Yes.
And in fact, I really want to do the following. Well, no, I don't want to give away the punchline. So, Thank you, that's right. What do I want to do?
You can put round brackets around this.
Yeah, I will do that later. Let me leave it like this. Okay, let me just do it like this.
Outside, you can put the digit outside.
Yeah. Let me just do this for now. So I'll come back to this point. So for P2, this is y prime squared minus 4y cubed. This is going to be P2 intersect. Again, I'm going to get y here, but in this situation, the lowest powers, the lowest homogeneous term is this, y prime squared, and it's not of that form. So what happens is this isn't the singular component. It's a prime ideal that contains the ideal generated by P2, but it's redundant. So in fact, it contains this. So this really is just this. This is a prime ideal. So the question that I want to pose is, what's the relationship so again, now I'm going to restrict myself to first order differential polynomials. I'm assuming, I'm not going to say it, but from now on, it's always algebraically irreducible. And the question is, what is the relation among the following? The LowPower theorem, to singular solutions. By the way, a singular solution is a solution of the equation that is also a solution of the separate. So, singular solution as envelopes versus parts embedded in families. And 3, generators for this. That is, I'd like to write this as the radical ideal containing a certain fixed set of polynomials.
Michael, what do you mean by embedded in families?
Just think about what I'll give a formal definition, but think about what I had before, that somehow it's the limiting case. There's a one parameter
you
family.
don't mean it, that there's a value of the parameter for the general solution. And you don't
Yes,
mean it's
I
in the
do.
parameter.
I do mean that.
It can be in the general component without being part of the
No.
classic. Really?
So let me say what it is. So I really mean there's a family of solutions such that for a one parameter family of solutions such that for one value of the parameter I get this, and for the other I get solutions of the general component, non-singular solutions.
You're still in n equals 1, right?
I'm in n equals 1 and first order.
And first order, yeah.
So it's a very small case.
I hate that. Is it inappropriate to ask the definition for the quotient ideal again? I mean, it's one of the things that I never read.
Sure. It's the quotient. It's the set of guys that, when you multiply by this guy, lie in here.
Okay. I get.
So things in this thing are things in here divided by that.
Right. Okay.
That's not true.
Right. I understand the motivation.
Okay. So, I'm going to be talking about solutions here. And so to make sense of envelopes and things like that, I really should be talking about functions. Right? So to explain this part, I'm going to be in what people derogatively refer to as the analytic case. Why people feel that's such a horrible thing. But nonetheless, really the result will be an algebraic result. Having said that, throughout what I'm going to say, at various points I should really justify that certain things are analytic, that they're analytic in certain sets, that I can shrink domains of definition and make sure that things are analytic. But I'm going to ignore that because it's boring. But important. So let me say the low power condition was that P is, what did I have? PR plus PR minus 1 plus PS, where PS is just the power of Y. A little less. Okay? So that's, if I say the low power condition holds, then that's what I mean.
C one and yes.
C1.
Oh yeah, sure.
You can always make it 1.
So,
Not 0.
Low power versus envelopes. And the result is the following. Y equals 0 is an envelope of non-singular solutions if and only if the low power condition holds. So there, already we're beginning to see that it has some analytic meaning. And if the low power condition does not hold, then, let's put it this way, does not hold if and only if y equals 0 can be embedded as part an analytic family of solutions okay, let's just say that. And of course, I'm assuming that P of 0 is 0, that it actually is a solution. I don't want this to be 0, for instance. Okay, so this is the this, and this is the result that bothered me. I'd never seen a proof of. So this is due to Hamburger in 1893. And it's one of the, so at the end of, well, in fact, throughout the 18th and 19th century, people were struggling with the notion of a singular solution. There were several definitions proposed. People would show that, well, that's not such a good definition, maybe something else. And I have a feeling this in many ways motivated Ritt to look at this. And when he wrote his 2 papers about the low power theorem, he quotes this result, but he doesn't include a proof of it. And Hamburger's paper, well, after going through what I'm going to go through today, I can see that this is what Hamburger was doing, but I could only see it after I kind of did it myself. So that's why I'm saying this perhaps isn't as original as I'd hoped it would be. Finally, what about generators? Up. Well, this is another theorem of Ritt. And again, I'm just looking at first order equations in one variable. But now I want to assume he has degree n in y prime. And I want to consider the algebraic ideal. So now this round brackets is just algebraic ideal, p probably n minus 1, in the ring of algebraic polynomials and let's say that this is u1, 2, ul, then this is this radical ideal generator for these guys. Okay. So that's Ritt's theorem. So he gives you generators. He says the key is that to get generators of this guy as a radical ideal, you only need to go as, there are too many n's here. No, they're not. You only need to go up to the degree of y prime in P. And, you know, this is far from correct in any other case. The buck stops here. But it's still a nice theorem. And Cohn, the paper that I'm going to use, Cohn wanted to give an algebraic proof of this fact. And he does. By the way, this relationship between envelopes and the general solution, it doesn't work for higher order. You can have second order equations where y equals 0 doesn't correspond to a singular component, but it also isn't part of a family. And of course, Ritt gives examples. It's hard to find an example of some phenomenon that wasn't known to Ritt.
Is it bound in sharp?
Yeah, so the first example is the sharp case.
But like in for every n?
Oh, I don't know.
Oh, it's
For n equals 2.
yes.
Actually,
N equals 2, yes. Degree 2.
yeah.
Yes, degree 2.
Yeah, okay. Well, you'll see from the proof that it probably is, but I don't know. So what's Cohn's method is based on Poiseuille series, Newton polygons. And let me remind you of what this is. Some Cohn's method. Oh, perhaps I should say this theorem was also proved by Cohn in Proceedings of the AMS, 1976. volume 55, number 1, and it's a 3-page paper. Very nice 3-page paper. So Cohn's method is based on Puiseux series and Newton polygons. So let me remind you. So if I have some polynomial, now this is just the usual polynomials in 2 variables. Let's say that K is algebraically closed. So the Newton polygon regrettably, if I were king of the world, I wouldn't do it this way, but this now seems to be the way it's done. You plot the points ij, where aij is not 0, and you take the lower convex hull. So by that I mean the following. You plot a bunch of points, and you start here, and you start swinging the vertical line out until you hit your first point. Then you do the same thing again. And you keep going. Okay?
So lower means you're swinging from below. So.
Yeah, right. I don't want to give a formal definition, but you can imagine what you just do this. Then you want to look at solutions of this in formal power series. Okay? And the result is that for each boundary line,
Are you using round bracket here? Rational?
excuse me,
Power series. You said power series?
it's rational, in fact.
Rational, okay, okay. Yeah.
Rational. Finite number of negative terms.
Okay.
For each boundary line Li, with slope, let's say, ui, f equals 0 as a solution of the form u is some constant the ai plus higher order terms. Actually, what I just said is not, yeah, this is right. Okay. And v is this. Terms where bi over ai is, and this is the part I hate, minus 1 over the slopes. Now, just a little word of caution. This certainly is a rational number. These points have integer coordinates. This doesn't have to be these don't have to be relatively prime. In fact, in general, they're not. You might need 6 and 8 here to get 3/4, okay?
So there's a choice there, you're saying?
I'm saying there exist, given this,
Yeah.
there exists
right.
things like this. I'm not going to say about the higher order terms. So in particular, these lines with negative slope correspond to solutions in the ring. and the lines with positive slope, you may need negative terms. So if I'm interested in things that start with positive, I have to look at this side. Okay. Should I give an example, or is this? Yeah, let me give an example.
Yeah.
So here's an example. E to the fourth minus u plus e cubed, e squared, plus u to the fourth. This is my f. Okay, so I certainly have, so uv would be 0, 4. I get nothing here when v is squared, 2. I'm sorry, I get here when uv. When v is 2, u can be 1, or it can be 3. And then when v is 0, I get this point. Okay. And the lower convex hull is this. So this was 0, 4. This was 1, 2, 3, 2. This is 4, 0. And the slope here is minus 2. Slope here is minus 2/3. Okay. And so I'll get 2 solutions. So u and v, one will be of the form, in fact, in this case, so minus 1/2 is minus 1/u1 is 1/2. The if I get it backwards, yeah, 2 goes here, 1 goes there, and the other one is something t squared, something t cubed. Okay. And in fact, if you factor this, the polynomial f was cooked up to be v squared minus u times v squared minus u cubed, and sure enough, v should be the square root of u, and here v should be the square root of u cubed, and that works out. So in fact, they're not going to be higher order terms. Okay, so that's the story of Newton polygon and how one solves polynomials in power series rings.
Excuse me, whose theorem is this?
This? Newton's.
Oh, it was Newton. Okay.
That's serious.
Yeah.
Okay.
Okay. Let me erase my example. Okay. Work it out again. So what was Richard Cohn's idea? So Cohn's idea is the following. You turn power series solutions of P of uv equals 0 into solutions of P of y prime equals 0. That was the idea. And in fact, if you, well, in this low power theorem business, power series methods are ubiquitous. I don't know of any proof of general stuff that doesn't involve some power series expansions. So this is the ideas. So what do I mean? What I mean is I want to find the derivation D on this field such that du equals v. And then for that derivation, p of u du is 0. Okay, it's a simple idea. Well, how do I do that? So if I'm looking at k of t, this was a differential field. So let's say d is the derivation on k. And there's another derivation on this field. It's the derivative with respect to t. Derivation on kt. So I'm going to define a new derivation. Okay. So for say f t, I'm going to define df to be, and I'll explain what I mean, this plus h df dt, where, let's say f is summation ai t to the I, df, I just differentiate the coefficients, df dt is summation I ai minus 1. And h is to be chosen. And how do I select this? I'm going to assume that du dt is not 0, because it's a non-constant solution of this, and that will be the situation I'm in. And then I'm going to select h such that du, which is du plus h du dt, is v. And as long as this guy is not 0, I can do that. So that's it. That's the idea. So what does this low power condition mean in terms of this h? So this is the key lemma, which is, Kohn doesn't state it. He only needs a little piece of this, but he makes noises that it becomes clear. He must have known this. So I'm going to let this h that I've chosen be this. And he, since I'm, use t. as before. So if the low power condition holds,
You mean R.
excuse me?
You mean use R, not T there. Subscript.
Thank you. Yes, then D is less than or equal to 0. By the way, assuming that's the Eigenvalue. PS is not of this form. Sorry. Be more careful. Then there exists solutions U, V, P of U, V equals 0, such that when I use those, V is positive. This is a V. So this is the meaning of the low power condition in this setting. It says that when you kind of naively solve the equation, set up a derivation, if the low power condition holds, then this will be this, otherwise it will be that. And I should say, there's one other thing that I want to say. I should have said this earlier. Say it. I'm only interested in U and V that lie in the ring. So in this condition, if this be this, and U and V, the U and V that I've chosen, let's assume I can choose them in here. That will always be the case. So I'm adding the assumptions. And let me prove a part of this.
You would have also to in the there exists UV, you have to say that partial U partial T is not 0 as well.
Excuse me?
You have to say the partial U, I mean, when you find U and V, you have to say that partial U partial T is not 0.
Yeah, right.
Yeah.
It will be the case. So let me give you an idea of the proof. So let's say that we have this. Okay. Now I'm going to draw this Newton diagram, but I'm going to draw it instead of just randomly putting points. I'm going to put down the points for the homogeneous pieces one by one. So what does that mean? That means U plus V equals S, and then S plus 1, and so on. Right? And the low power condition is that, by the way, this isn't a T, this is, of course, a U. Sorry. It's a polynomial in U and V. So, what points can lie here? There's only one point, and it is here. It's the point 0, S. I'm going to take this away. All the other points, all other points lie above u plus v equals s.
Oh, yeah, it does. It does. Well, he means the line. He means defining the line.
So I'm just looking at I'm graphing the exponents, right? And these are the ones where the exponents add up to s.
Right. So
that's that line.
yeah.
And the others will be parallel lines going
Right.
out.
Right.
So a little thought, one can show that there have to be points to the left. So my Newton, if I normalize, my Newton diagram will look something like this. Looks like they're all on one line, but I don't want that to be the case, so I'll break it a little bit. So remember, the things with negative slope correspond to negative slope, correspond to solutions in here. Yeah?
Wait, I'm sorry, R is less than S, right?
No, bigger.
Bigger.
Oh, okay, now it makes sense, okay.
So R minus 1 dot 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 to S.
Oh, right, of course.
Okay?
You're right.
So, so what does this mean? These lines, this has slope minus 1. Right?
Yeah.
These lines have slope less than minus 1. So these mu's are less than minus 1. 1 over mu is bigger than minus 1, and minus 1 over mu is less than 1. So when I write minus 1 over mu as try and keep the notation a little consistent. B over A. U is something t to the A. B is something t to the B. And I had D of U. This was V. So this is du plus H du dt. Well, if A is this summation A on t to the I, if I take the derivative of the coefficients, the order, the lowest degree term, the lowest degree term might vanish. So the next term may appear. So what happens, and I'm going to call this the order, the degree of the lowest power that appears, on this side, it's going to be at least A. It could get bigger. Here, this has order D. This is going to have order A minus 1. And again, these will be, this won't be 0. So it's some positive thing, so it goes down by 1. And on this side, it's going to be B.